And as has been discussed, if you're not doing anything tonight, you're really hard up for entertainment. I'm doing the presentation about 7:45 at the Mays Board of Education, so if you're not doing anything, what might?
Where is that building located at?
It's at, okay, if you're on 119th, okay, and like you're going north.
YCA, right? Where's that?
Huh?
On 119th, big
You're
man.
going
119th
north on
right here.
119th. Like if you're at 45th and 119th,
Okay.
and you're going north, okay, you're gonna run into a street called Academy.
Yeah.
Okay, you can take a right, and it's gonna be the first building on your right.
Okay. I think I know where that
Yeah,
is.
it's
Like,
close.
Right before
like down the road. Oh, yeah, why
Before
was
Broadway.
Yeah, right before
Broadway.
Yeah.
No, it's weird, because
Alright.
like that doesn't show up on Google, because like they changed the street name to Academy, and Academy hasn't like been updated on Google, and it's just kind of weird how that would goes.
Didn't they change the name like 4 years ago though?
Yeah.
They changed a
Yeah,
long
because it
time
used to
ago.
be
Yeah.
Central.
Yeah,
Yeah,
it was
but then they were
I mean, how
confusing
often
that
does
central
Google
with the
pay
central in
attention
Yeah,
like
like the guy
Wichita.
like died.
Yeah,
Wait,
and-
what? Where did some guy die?
because they confused the central
ambulance, like,
in
went to
Mays
go to
with the
Central and went
central
to the
in
wrong
Wichita.
Central, 'cause there was another
Oh,
central.
okay.
Yeah.
Oh, okay. All right, anyway, back to our story.
Oh.
So anyway, so not doing anything, it'd be great if you do it. Okay, any questions on the assignment?
Next year.
Okay, you can't do 17 unless you do 16 first, okay? So, there's any number of great conservation laws that exist in science. One is the conservation of angular momentum, okay, which is what is happening here. And you also have linear. Now, here's the beauty of every one of these problems, is that they all start the same way. The sum of the momentums before have to equal the sum of the momentums after. And if you don't know what the sums are, then you're screwed right from the beginning. Okay? That's just a cold hard reality. So if it's angular, you're going to talk about the sum of your L's is going to equal the new sum of the L's. If you're talking about linear, it's the sum of the momentums has to equal the new sums of the momentums. Okay? They all start the same way. So on 16, all I'm asking you to find is the angular momentum of the spinning sphere. So to get angular momentum, what two things do you need?
You need your omega.
You need your omega and you need
You need
your moment of inertia. Okay? So basically it's the resistance to a change in velocity multiplied by how fast you're spinning. And that's true even if it's linear momentum, because it's momentum is mass times velocity. Now, let's talk about this I. What's the only time you can let I equal mr squared? There's only two situations.
point mass.
Point mass or a. If I do not tell you it's either one of those, then you have to use a specific formula. They're on the back side of your equation sheets, okay? So don't memorize them for the test. I'll always give you whatever moment of inertia, that equation that you're going to need. But here's what's important. No matter what are the moments for moment of inertia? What are the units for any moment of inertia? Kilograms meters squared, okay? It doesn't make any difference, they're always kilograms meters squared. So this is always going to be kilograms meters squared per second. Technically there's radians in there, but that's a dimensionless number. So, on 16, you've got 30 revolutions per minute. What are you going to do with the revolutions per minute?
Convert that to radians.
Convert it into
Radians.
radians per second. And if that's wrong, everything else in this problem is going to be tanked. So, your radians per second should be 3.14 radians per second. Okay, so when you convert the revolutions per minute into radians per second, that's 3.14. So your answer to 16, because if 16 is wrong, 17 is going to be a train wreck. So your answer to 16 should start with a 4, and it should be something times 10 to the negative fifth. Okay, it's a very small, it's like a ping pong ball that's spinning. Okay, so this is a very, very small number. Okay, so on 16, it's going to start with 4, something times 10 to the negative fifth, kilograms meters squared per second. Now, here's what's going to happen on 17. And I beg of you, start these problems the same way. Because I promise you, listen to me, there's going to be a problem like 16 and 17 on the test tomorrow. I promise you, it is going to be on the last page of the test. That's where it's going to be, okay? That's where this question is going to exist. So don't think, oh, I don't have to know this. I'm telling you right now, this problem is going to be on the test, okay? So in this situation, you've got the L of the bug plus the L of the ball has to equal the new L of the bug plus the new L of the ball. Okay? That's the way this deal has to play out. Okay? That's how you start every problem. Now, is the bug part of the system
No.
initially?
No.
No. So you don't have to worry about that, so that's 0. Okay? You don't have to worry about that. Now, you already found the angular momentum of the ball. You already know that number. You found it up on number 16. There's nothing to calculate. You already have this number. So that's like 4 and some change times 10 to the negative 5th kilograms meters squared per second. So you already have this number, but don't recalculate it. You already know what it is, because that's the total angular momentum of the system. Now, here's the question. Is the bug and the ball going to spin at the same rate?
Yes.
Yes, because the bug lands on the ball. He's not walking backwards or forwards. The bug's just there. Okay, it's just what bugs do. They're just there. So this is like the California spin, okay? Instead of the California roll where they move off together, this is the California spin, so they're going to be spinning at the same rate. So if this is the case, okay, since they're spinning at the same rate, what can you do?
Factor
You
out.
can factor out butt prime. So this is going to be the I of the bug plus the I of the ball times butt prime. Okay? Now, here's the deal. Think this through before you do any calculations. At what rate was the ball initially spinning at? 3.14 radians per second, right?
Yeah.
So when you find butt prime, what does that have to be less than?
3.14.
3.14. If you get an answer bigger than 3.14, you have done something wrong. Okay? Now, you already know the I of the ball. You found that up on 16. It isn't the angular momentum, but it's the moment of inertia. So you already have this number. Now, how are you going to treat the bug?
It's a point mass.
It's a point mass, which means you can use
MR squared.
mr squared. Now, what are you going to use for the radius?
You use the radius of the ball.
Okay, you're just going to use the radius of the ball. Okay? So, you're going to find this number, add it to the I of the ball, so you get the I of the bug plus the I of the ball. And the only thing you don't know is that new rate of spin. So if all goes well, your answer to number 17 should be between 2 and 3 radians per second. Yes, ma'am.
On 16, I got 10 to the negative third. But I got the same, I got the right answer on 17. But I assume it to be right.
There's no way you did. There's no way. You changed the grams and centimeters into kilograms and meters. Yeah.
And then 0.3 meters.
No, 0.03. Because it's 3 centimeters, and you divide that by 100.
Oh, okay, I see.
That's why you're off by 2 decimal places.
Okay.
And then it gets squared, and that makes it even worse. Cool with that one? I promise you, there's going to be one like 16 and 17 on the test tomorrow. I promise you. Okay? Felix, we good?
I'm fine.
You sure?
He's a little confused, Bert.
On what?
Well, like,
He's
Like
confused
the
on
other.
the eye of the ball and the eye of the bug.
yeah,
Okay.
because like I got 3.14.
So the eye of the ball, right? Because it's a hollow sphere, I told you you're going to use 2/3 mr squared. So that's just plugging in numbers. So for the eye of the bug, though, because that's a point mass, you're going to use mr squared.
Oh.
Picking up what he's putting down.
Yeah.
Now, if you really wanted to get fancy, okay, if you really wanted to get fancy, what you can do here, because that's 2/3 mr squared plus mr squared, so you could factor out like an mr squared and multiply that by 2/3 plus 1, otherwise known as 5/3, if you don't want to get fancy.
I just keep it simple.
Okay, or you can just keep it simple and find each problem, each one by itself. But I'm just saying, if you wanted to, you could. That's the fancy way to do it.
You get extra credit for that?
No. Now, on 18, okay, again, I tell you on 18, you're treating the moon as a point mass, okay? You're treating it as a point mass. Problem is that there's a whole bunch of things that you don't know. But on 18, here's what you got to do. You're going to use L equals I omega. For the I, you're going to use mr squared, okay? Now, the problem is you don't know the rate of spin of the moon. Now, think about this. Do you think this value for omega, in terms of radians per second for the moon, is going to be a really big number or a really small number? For omega of the moon. In other words, as the moon goes around the Earth in radians per second, do you think this is going to be a big number or a small number for omega itself? It's going to be small. Look, how long does it take for the moon to make one complete revolution around the Earth? 27.3 days. It's only moving through 2 pi radians. Man, you're moving through 2 pi radians in 20. Imagine that, imagine that I've got, Shively's arm out here like this. And I'm telling you have to move so that basically 28 days later, you've completed one revolution in 28 days. He's not going to move very fast. Yeah, it'd take you 14 days just to get over here. Yeah. So, anyway, so if all goes well on 18, you should end up with something times 10 to the 34th.
Oh.
Okay, that's what I got, but,
On what?
17, so.
Really, what I want to do is ask about everything because I have no idea what's happening.
Divided by.
Do you get the right answer to that?
Yeah.
Plus 0.0000.
Don't look at my paper for answers. Look at analysis.
I'm looking for 16.
But before when I did it, I got 2.71.
We'll figure it out.
Yeah, so what's wrong?
I'm here to help you
Well,
out,
that
yeah?
was my calculations before, but then when I
What did
put
you
the
not get
different
right?
numbers, I don't know.
Really, what I need is more problems to go
Well,
over.
I'm not.
I just need to practice it.
1.1208.
Do you get this number 18?
Yeah, I understand that. I did that one right. I understand number 17 now, and really what I need is just problems to practice.
I got it.
That's where you're going south on the bud, because you're using 0.3, that needs to be 0.03.
Okay.
That's where it's going. That's where it's going south.
I just need to change that one.
Yeah. But again, because you're squaring it, that's why you're off by such a big number. 5 through 10 all build on each other. So if you get down to number 10 and you have an answer around 800, you're okay.
Oh, let's get, I don't know, for some reason, the velocity, the linear velocity for some reason just seemed too big for me.
When you're finding the moment of inertia, do you square it?
Is it around a little bit less than 100?
Yeah.
Okay, for some
But
reason,
it's also spinning really, really fast.
okay.
Right, yeah.
See, I was just afraid that I had done something where I trusted the oracle again.
No, you're fine.
Okay.
Okay, I got
Yeah.
the answer.
It's right there.
Okay. Anything else from the assignment?
Do you go through how you calculate the angular acceleration for 7?
Okay, this is what I would do. Torque equals two things. It equals Fr and it equals I alpha. Now, here's what you cannot do. Listen to me, listen to me, listen to me. Here's what you cannot do. You cannot take 8 newtons and say, oh, there's my force, and divide that by the mass and get 4 meters per second squared. So you cannot use F equals ma. And then go A equals R alpha. So you cannot do this, mainly because where you apply that force greatly alters your angular acceleration. So you cannot do F equals ma. Listen to me, listen to me, listen to me. Do not do F equals ma to get your linear acceleration. Okay? So at this point, you're going to know your torque and you know your moment of inertia. So find it that way. So yeah, you're on 7, your answer to number 7, and this is an ish, should be something around your current age.
Yeah.
That's an ish, but. Hunter. 14?
What'd you get on 7? What'd you
Okay,
get on 7?
so here's the deal, Hunter.
0 radians per second squared.
You know, L equals I omega, right?
Yeah.
Okay? So you got the angular momentum, okay? And you've got omega, so you can find the value of I.
The decimals always confuse me because you put a
Because
decimal
you know
point
L
to
and you know
make it
omega.
It's still just.
Now, because it's a solid cylinder, okay? How do you find the moment of inertia of a cylinder?
Which one is this?
13.
1/2 mr squared. So set that I equal to 1/2 mr squared. Not a problem.
And if it all goes well,
Your answer to 14, if all goes well,
should be less than 1.
should be less than 1 meter.
Yes.
Now, if you want to hold on to this assignment and hand it in tomorrow, you can. If you're done with it and you're feeling good about it, you can go ahead and hand it in. It doesn't make any difference. So,
Max, you want to hang it?
all right, so here's what we've got. So, on both situations, we've got a 100-gram mass suspended from the end of the string. Okay? Same cars, but Shively has 1,000 grams attached to his, and I've just got the card itself. So what we're going to do is we're going to let go of it, and we're going to let them roll for we're going to go 3, 2, 1, and then we're going to go 1,001, and then we're going to stop it.
Racing.
Okay? So, what do the two cards have in common?
The same amount of force pulling. Oh,
Same track, and the same amount of
force.
So I got 100-gram mass suspended on each string. So how much force is applied to each system?
Same.
Don't make this difficult.
0.98.
0.98 newtons, right? Okay, because 100 grams is 0.1 kilograms, 0.1 times 9.8, right? So do I have the same amount of force acting on each system?
Yeah.
Okay. So we're going to go 3, 2, 1, go, right? Then we'll go to 1,001, then we're going to stop it. Okay, so 3, 2, 1, go. 1,001.
Possible.
Okay. Good. Now, which one went further?
Yours.
Why did mine go further?
Because you know when to say stop.
Because I know when to stop. Okay, what'd you say?
It has a lower relative inertia.
Whoa. There's no rolling.
Just less inertia.
Yeah, it's just less
Not so much
inertia.
moment of inertia. Because that would be like if I was making like it spin.
Just less inertia.
So it can
But it's
get
less
going-
inertia,
it can get
right?
going
It
easier.
has less mass.
It has less mass. Is the same force applied to each system?
Yes.
So Garrett, which one's going to undergo the greater acceleration? Why? Because it has less inertia, right? It's easier to speed up. Okay, now, pull that back up. So, we had the same force acting over the same amount of time. So what else is common?
Time.
Okay? So what else is common? No.
The same change
No,
in
not the same
momentum.
acceleration.
Same change in momentum.
On the same change in momentum.
Oh, yeah, that's right.
Okay? Because force times time equals
Change in momentum.
change in momentum. So in that calculation, the fact that Shively's cart has 1,000 grams more than mine, is that a factor in your force time calculations?
No.
Because it isn't the weight that's acting, it's the supplied force. So we'll do this again, right? So we're going to go, ready? 3, 2, 1, go. 1,001. So mine went farther because it was the same amount of time, right? But I had a bigger acceleration, so that with the same amount of time, I traveled a greater distance. So, now, that's good. Now, let's look at the math. Let's go ahead and pull that back up. So here's the setup. So what would a force time graph look like, assuming that 1001 is 1 second?
The horizontal line.
Horizontal line where?
0.96.
0.98 newtons, and that's going to be for
1 second.
1 second. Will that be the same for both carts?
No.
Yes. Yes.
Yes.
Yes.
Yes?
Yes.
Yeah.
Why?
They have the
Same force at the same time.
They have the same change in momentum,
Yep. No, you're not.
right? Same change in momentum. So would, if you were to look at a momentum time graph, what would that look like? Where's it going to start?
0.
0, 0. Because the cart started at no momentum. So what's it going to do?
It's going to slope up.
Slope up. At the end of 1 second, how much momentum does it have?
0.98 seconds.
Why 0.98 newton seconds?
It's the area of,
Olivia, what'd you say?
it's the area of the force time graph.
Ah, so if I were to find this area, by taking 0.98 times 1 second, I'd get 0.98 newton seconds. Okay. So at the end of 1 second, I'm at 0.98 newton seconds. It's going to come up here like this. So what does the area under a force time graph give you?
Momentum.
Momentum. But what does the slope of a momentum time graph give you? Force. Because if you notice, you're taking 0.98 newtons, seconds, dividing that by 1 second, seconds cancel out, I get 0.98 newtons, boom, that's the force which is going to play out here. Now, what does the area under a momentum time graph give you?
Newton second squared.
Well, what are the units?
Newton second squared.
Newton second squared. What on God's green earth is measured in Newton second squared? Nothing. This area has no uses.
Wow, trick question.
It was a trick question.
You're so smart, Logan.
Okay? So, yeah, nothing's measured in Newton second squared. Now, here's what's important, okay? Even though I have different masses, do they undergo the same change in momentum? Yes. Now, if you were to look at, let's change this up. If you were to look at a velocity time graph, okay? If you were to look at a velocity time graph, would both carts have the same velocity time graph? No. Great. Which one would be steeper, mine or Shively's?
Yours,
Why?
because you have greater, you have greater acceleration.
So?
So your velocity is going to be, you're going to have more dollars.
Because I'm making more per second?
Yeah, you're making more dollars. You're going to have
It was over the same.
more spin.
Okay? Now, from a momentum standpoint, how do I know that my velocity has to be greater?
Because they're gonna be the same change in momentum and his mass is bigger.
So his has to be going slower. So my velocity time graph, so that's the smaller mass. So Shively's might be something like this, with a bigger mass. Now, what does the area under a velocity time graph give you?
Acceleration.
What does the area give you?
Displacement.
So does this verify the observation that you just saw?
Yes.
Why, Ethan?
Because yours has bigger or more displacement. So
Yeah. I
We
went
travel
farther,
further.
okay? So my area was bigger. So they ended up with the same momentum, but they didn't end up with the same velocity, and they don't have the same acceleration. Got it? Good? Okay, back we go. I tried it when I was in the Peace Corps, just
I knew
because
it.
I didn't have hot water, and I was just taking cold showers outside in the middle of the winter.
cold showers are
And said, okay, enough with the shaving, but it was horrible. It It was Mary.
Name patches?
So, huh?
Did you get the nickname patches?
No, and it was itchy and just
It
wasn't.
does get a little bit itchy, but once you get past the itchy, it's really warm.
I bet Benny with the chicken
Okay.
just solved that.
Literally Friday?
So let's say hypothetically that the mass of Gary the golf ball is 50 grams and the mass of Hank is 10 kilograms. Okay, just to make the math easy. So imagine that I'm going to hold them up both to the same height. Okay, and I'm going to drop them. Okay, I'll drop Gary. You get the idea of what's going to happen. I'm not dropping Hank. Okay, I don't want to explain how I cracked the floor.
Teach physics, remember?
I know, but even then, that would be a push. It's like, we can't really. So, now, I'm going to hold them to a certain height so that they both fall for a half a second. Okay? Both going to fall for half a second. So, Mary, at the end of a half a second, how fast is each one of them moving?
Same speed. Or, yeah,
Huh?
the same speed.
The same speed, but how fast are they moving?
Fast.
Fast. Okay, because if I just drop it from this height, that's not so fast. But if I drop it from here, that's fast. So if I held it from the ceiling, that would be very fast?
Yeah.
Sure.
Gotcha.
Do it.
Very.
Do it.
Acceleration.
No. Okay.
Oh.
4.9.
So shh. Mary, what if they fell for exactly 1 second? How fast would they be moving?
9.8 meters per second.
Exactly. So if they only fall for a half a second,
4.9.
4.9, nice.
That was good.
Okay.
That was good. I like that.
It's nice, right? So, if they both fall for a half a second, they're each going to be traveling 4.9 meters per second. True? So what we're going to do is contrast this with what we saw back there. Okay? So I got Hank, I got Gary. I'm going to drop them both. They're both going to hit at 4.9 meters per second. So what would the velocity time graph look like for, that's velocity, each one? Would it start at 0?
Would head down.
Go up to 4 point.
Well, you want down to be positive or negative.
Let's make it negative.
Negative.
Okay? So that's going to be negative 4.9. So it's going to start at 0 and it's going to come down like this, right?
Correct. Once it hits the floor, it's kind of immediately kind of jolted back up.
So would they both have the exact same acceleration? Yes, right? And they would both land at negative 4.9 meters per second. True? Everybody cool with this? We're good. Okay. Now, so they're both going to land at negative 4.9 meters per second. This has a mass of 50 grams. Tank has a mass of 10 kilograms. So even though they're both going to land at the same velocity, are they going to have the same momentum?
No.
Which one's going to have more momentum, Bree? Hank or Gary? Or will it be the same? Bree, what does momentum equal?
Force times time.
But it also equals?
Inertia times angular.
No, you're making this way difficult. What's the simplest way to calculate momentum? What times what? Velocity times?
Oh, mass.
Yes.
So the Gary would be smaller.
Yes, because he has,
Less mass.
but it has the same,
Velocity.
yes. Okay, so they're both going to land at the same velocity, right? So Gary, since they're both going to land at negative 4.9 meters per second, which is fast, Mary, which is fast.
Yes, it is fast.
It is fast. Okay, not very fast, but it's fast. It's fast. Okay? So if I take negative 4.9 times 10, I'm going to get, you are not going to touch a calculator to do that calculation. Negative 49 Newton seconds. Cool with this. Now, legitimately, we can use the calculator on this one, because 50 grams is how many kilograms? 0.05 times negative 4.9 gets me negative what?
0.245.
Negative 0.245
Yeah, correct.
Newton seconds. So here's the $1 million question. What would this momentum time graph look like?
They'll both start at 0?
Both going to start at 0, but will they have the same slope?
No.
Why not?
Because they're in at a different moment at the same
Different
time.
momentum over the same amount of
Yeah.
time.
So if you're out here at a half a second, Hank is going to end up down here at negative 49 Newton seconds, right? So he's going to end up way out here like this. Where's Gary going to end up?
2.4.
Negative 0.245, okay? Gary is shallow as a freshman, you know. So,
It's not nice.
oh, I'm just telling. So, he's going to end up here.
That's all I'm saying.
Basically something like that, right? Now, could I find the slope of each line?
Yeah.
Yeah.
Sure enough.
Sure enough. What is this? Howdy Doody goes to physics?
Absolutely freaking would. I love physics.
Okay. So, what would the slope of the momentum time graph be for Hank?
Would be negative 49 seconds over 0.4. All right.
So, here we go with Hank. So, we're going to take negative 49 Newton seconds
Over
and divide that by a half a second. And we're going to get what?
98.
Negative 98 newtons. Why?
Because the seconds cancel.
I know that, but why do we get negative 98? You're right, the seconds do cancel. That is a beautiful answer. That's why we get the units. But why do we get an answer of negative 98?
Mass times velocity.
Oh, what's the force? If Hank has a mass of 10 kilograms, what's the force acting on a 10 kilogram mass once you drop it?
98.
Negative 98. Oh, that's kind of cool. Okay. Oh, that's the force acting on it, right? So, the slope of this line is going to be negative 98 newtons. So, somebody take 0.245 and divide that by 0.5.
0.49.
0.49. Wow, negative 0.49 newtons. Why?
No way.
Seriously, step back.
You've got to.
That's the force acting on it.
Oh, nice. Now,
So it's 200 times smaller.
whoa,
Yeah.
whoa.
Yeah.
Why?
Because it's 200 times less than.
No, keep going.
Less than mass.
There you go.
Proportional, right?
Yes.
Oh, I did not know that. Okay.
Nicholas,
Whoa.
let's go.
Well done.
Okay. Now,
He's nuts. Someone's
what
fine.
would
That's crazy.
the force time graph look like for each one?
Would it be? Would it be a horizontal line for each one?
I don't know.
Yeah, two separate,
Give it
two
a-
separate horizontal.
So, one force, so you got Hank at 10 kilograms, right?
Yeah.
So 10 times negative 9.8 gets you
Negative 98.
negative 98.
Got it.
Okay? So that's over here at negative 98 newtons, and that's going to be for
0.5 seconds.
a half a second.
Thank you.
And that area would equal what?
Just pretty much.
What would that area get you?
Change in momentum.
If you take negative 98 times 0.5, you get
Negative 49.
negative 49. Whoa. Which is your change in your momentum. Whoa.
Whoa.
Now, if you take Gary the golf ball, because we said his force was what? Negative 0.49? If you take negative 0.49, which is going to be this really shallow thing, right, going on here, okay, times a half a second, you get negative 0.245. Which is that change in the momentum? Oh. Okay? Now, so here's, I showed this to contrast two different ideas. What we did in the back, we had the same force acting over the same period of time. And we got two completely different velocities, okay? Because we had ended up with two completely different accelerations, but they had the same changes in momentum. But when you drop two objects of different mass, you end up with the same velocity, you end up with the same acceleration, but the changes in momentum are completely different, okay? So that's the fundamental difference between the two of them. Now, if you go back to what Shively and I did, okay? So here's Shively's cart, okay? And it had the 1,000 grams on it. And here was my cart, right? If I wanted Shively's cart to have the same acceleration as my cart, what would I have to do?
Give it more force.
Yeah, I'd have to put a lot more mass out here on the end to get that. So I'd have to have a more force to end up with the same acceleration, which is why there's more force acting on Hank from a gravitational standpoint to get the same acceleration as there is on Gary. Okay?
Okay.
Makes sense. We're good. Now, so let's talk conservation of angular momentum. So what are the two factors that play into
Your moment of inertia.
L is going to equal
Moment of inertia
I
times
vote.
omega.
So let's revisit this in terms of Kepler's third law. Okay? Now, we're going to do a little bit of hocus pocus. But not much. A little bit. So as our rock orbits our star, how can we treat our rock in terms of the calculation of moment of inertia?
A point mass.
Point mass. So how could we talk about the moment of inertia of the Earth? What would we have to know?
Mass and
Mass
radius.
and... Now, would we use the radius of the Earth itself or the distance from the Sun?
Distance from the sun.
Distance from the Sun. Okay? So that's going to be mass of the Earth, r squared, right? This is a point mass going around. It's kind of cool. Okay? Now, let's talk about omega, okay? So, do you think, in terms of omega, the Earth is moving very fast in terms of radians per second as we go around the Sun? No.
No.
No, okay? Or not? So, thank you. Now, in round numbers, if you consider the Earth to take a year to go around, okay, it's about 360 degrees, okay? Earth is about 360, a year is like 360 days long, roughly. So each day we basically move through a degree, okay? As we go around, we move through a degree. So if you look at this in terms of omega, right? So omega is going to be measured in what units? Radians per second, right? So let's talk about that. But when you look at Kepler's law, when you look at Kepler's second law, did he talk about a velocity in radians per second?
No.
He was talking about like a linear velocity and how fast it was moving. He wasn't talking about radians per second. So last week we talked about this equation, where V equals R omega. So here's the question. Could I solve this for omega and substitute that in there?
Yes.
Yeah.
I think so, seems reasonable, right? Okay. So I got V over R equals omega. True?
Yeah.
So if I came in here and said, okay, that's the mass of the Earth, R squared times V over R. Go with this idea.
And then
All I did was a simple substitution. But what's going to happen to one of the R's?
they're gonna go away.
It's going to cancel out. So I got mass of the Earth times,
Radius times velocity.
yeah, so I got Mr. V. Not confused with Mr. T, we've got Mr. V. Now, that's going to equal L. Okay, that's kind of cool. So, do you think angular momentum stays the same as the Earth goes around in an elliptical orbit?
Probably not.
No, there's no roughly to it.
No, because the radius is changing.
Hold on. Does angular momentum have to be
Oh,
conserved?
yeah, it does, because the radius changes, but the velocity gets faster.
Now, here's the whole kicker. In an elliptical orbit, your angular momentum has to be conserved, okay? L has to be conserved. There's not kinda, okay? This is like, does gravity work kinda? Maybe, I don't know, okay? So here's what I want to look at. So I've got L equals Mr. V. So
Shut up. I
in this
actually got to the
elliptical
right answer.
orbit, L is going to stay the same. So I got mass, and I got mass. Mass of the planet as it goes around. Okay, that's kind of cool. So here's the deal. So when this radius is smaller, what has to happen to the velocity?
Has to be big.
It has to be big. And then over here, when the radius gets bigger, velocity has to become
Smaller.
smaller. That way you can conserve angular momentum. So the other way to view, and Kepler at the time didn't know anything about conservation laws, angular momentum, anything like that. They didn't know anything about it. But once they realized that angular momentum had to be conserved, then this is how you could also explain the observations and go, this is why it had to work. You had to conserve angular momentum. So when you have a small radius, you have a bigger v. So the same thing happened. Who spun on Friday?
I
I
tried.
did.
You
I
tried.
did in the chair.
Okay, so here's the deal. So this is the same reason why it's black holes, whether it's a hurricane, whether it's a tornado, whether it's an ice skater. Your angular momentum has to be conserved. So when the radius becomes smaller, what has to happen? You have to spin faster, okay? This is why it's such an important conservation law. So if you look at like a big massive hurricane, okay, here's the eye of the storm. Where do you think the strongest winds are going to be?
Closest to them.
Closest to it, okay? So that you conserve that angular momentum. Neutron stars, whatever it is, your angular momentum has to be conserved. And it's true even if you go down to like the atomic level. If you look at electrons, okay, electrons have to conserve angular momentum. So no matter what scale you take this to, this value has to be conserved. So then they said, oh, now we know why Kepler's laws work. Because Kepler at the time said, hey, I don't know why, you guys figure it out. Here's the story. Okay, so we're cool with this. Now, let's talk about one problem that I promise you will be on the test. I promise you, and it's on the review. The problem where you hold a ball up, and you drop it, and it hits the ground. Okay, we work through that big complex problem. So roughly, what's that velocity time graph going to look like, assuming that down is a negative value?
Start at 0.
It's going to start at 0, and it's going to do what? Go down with the slope of negative 9.8, and I'll make it on the Earth. I won't do anything weird and put it like on the moon or anything. Okay? Then it's going to hit the ground, so then what's it going to do? Shoot up.
And it'll go above 0.
Okay?
Past it, yep.
So is this value going to be bigger or smaller than that velocity?
Smaller.
Smaller. So this is when you're going to hit, what's gonna happen up here?
You leave the
You're gonna
ground.
leave the
You're
ground.
gonna leave, and then it's gonna do what?
Slope
Slope
at
down
negative
at negative
9.8.
And that's gonna be, these two lines are gonna be parallel, okay? Guaranteed, if you get done with the test and you haven't drawn a graph like this, you have done something wrong, okay? Now, I'm not gonna expect you to find the actual times, but I am gonna expect you to be able to work this big deal. And here's the whole kicker. You gotta just change the momentum as mass times V minus V naught. And this is what's gonna screw you up more than anything. You're gonna lose track of which one is V and which one is V naught in terms of this collision. So, this impact when it hits, is that gonna be V or V naught?
V. It's gonna be V. V not. It's gonna be V. Yeah.
I want the change in momentum when it's in contact with the ground. The velocity when it hits is gonna be
V naught.
V naught. The velocity that it leaves at is going to be V. Now, you're gonna use V equals, you're gonna use that equation, but here's where it gets a little bit weird. When you find V naught, that's gonna be V. When you find V, that's gonna be V naught. So that's a transition that you have to make. You can sort through it. Now, again, you all know this equation is going to be on the test, okay? Or this problem is going to be on the test. You know it's going to be on the test. There's a problem like it on the review. Work this problem again and again and again, okay? Because you know it's going to be there. Change the numbers. Now, on the test, I'm going to tell you straight up, you're going to have to show me all the calculations. So let's say you have something like this. 2 times negative 9.8 meters per second squared times 1.2 meters. So you got 2 times negative 9.8 meters per second squared times 1.2 meters.
Not gonna
Why
work.
will I flip out?
Because your 1.2 is a negative.
You've got a negative underneath the radical, and I will sarcastically write, wow, imaginary velocity. Wow, imaginary points. I won't do that, for all take it. So, here's what how can you fix it?
Make the displacement negative.
You can make the distance negative if it's falling down.
Make the reference point
Okay.
where it's dropped.
No. I'm going to tell you the truth. The reference point is going to be the ground.
Yeah.
Reference point is going to be no. No. Great. No. Now, the other thing that could happen, like it could be that it's 0 squared minus 2 times negative 9 point times 1.2.
Why don't we take this
So,
on the regular?
if you have 0 minus this quantity, then that's cool. But, so this is why you have to pay attention and make sure that you show this calculation. Now, let's say that you're going to have a spinning wheel, okay? And you want to make that wheel spin. You got it on a stand. So what are some things that are going to impact the rate at which this bicycle wheel spins? So if I said, all right, hey, what are some things that will impact that acceleration?
Radius,
Of what?
the point mass.
The force of
Okay? So Greg's saying the radius of the mass. What will the radius of the mass impact?
It's acceleration. Or
Inertia. Not inertia. Close. Moment of inertia. So where the mass is located is going to affect your moment of inertia. Because, again, let's say that I take this same wheel, okay, the exact same mass, and I compress it down to a wheel that's only like this big. Compress it down. Would it have the exact same inertia?
Yes.
Yes, it would have the exact same inertia. Would it have the same moment of inertia?
No.
It's smaller.
Why?
Radius is small.
Yeah, the radius is small. It would have the same inertia, but it wouldn't have the same moment of inertia. So, radius of the mass will affect the moment of inertia. Okay? What else will affect the rate at which that wheel spins? Force. Okay?
Oh, the rate, yeah.
Right? Because force is going to affect what? Well, it will, but there's something bigger. Because here's the deal. If I come out here and apply just a little bit of force, or if I apply a lot of force, what does that change? No. Rhymes with orc. Torque, right? Because force times radius gives me torque. True?
Yes.
So if I apply more force, I'm going to generate
More torque.
more torque. Okay? So the amount of force is important. What else could I alter about force that will impact the acceleration of that wheel? Where do I apply that force? Because if I apply that same force right here, okay, or I apply that same force out here, I get completely different accelerations. So not only is it how much force that I apply, it's where I apply that force. So not only is it how much, but it's also where I apply it. So could I generate the same torque by applying a force here as I do on the outside? But what would I have to do?
Increase the force.
Yeah, I'd have to apply a lot more force here. It's just like opening up the door. I can get the same torque, but I'd have to apply a lot more force out here to make that thing get the same acceleration as I do out there. Now, somebody else said one other thing. Not only the force, but also how long I apply that force. Do I apply that force for just a few seconds, or do I apply it for a long time? Say, do you tap your brakes, or do you really lock up your brakes? Okay. So keep all that in mind. Let me see what else. Let's say that you've got a block of wood, and a piece of clay is going to come along and hit the block of wood. So let's talk about changes in momentum, let's talk about changes in velocity, and let's talk about forces. So we're going to talk change in momentum, force, and acceleration. 2 of the 3 are going to be the same for both systems. Which ones? Force and? Why the force? Why does the force have to be equal and opposite?
Because it can't move, push. Because the block has to be given
Every
force.
action has an equal.
What's Newton's third law? For every force there is. Now, notice that does not say just on Tuesdays on a multiple choice test in Burkham's class. Okay? It says for every force there is an equal and opposite force. So your forces are going to be equal and opposite. What else? Changes, not momentum, but changes in momentum. Okay? Now, will they both also undergo the same acceleration? Shively, you shake your head no. Why?
So, wait, are they sticking together?
They're sticking together. Or they bounce off. It doesn't make any difference.
No, because the bullet will have more acceleration because it's like slowing down a lot faster.
Yeah, because F equals ma, right? So if you have the same force, the bullet has a much smaller mass, so it's going to go a lot bigger acceleration. Okay? So here's what's always true. Do not overthink this. Okay? Your changes in momentum are always equal and opposite. Forces are always accelerations are not. Are not. Are not. Which one will undergo the bigger acceleration? Small mass, large mass? Small mass. Okay. All right. So, now here's what worries me about this test. Is that historically, the test scores on this momentum test tend to be worse than the planetary motion tests are. And here's why. Okay, here's why. Is that I think you all think, oh, this is easy. Okay? And then you don't study as much, and then you get to the test, and then you get your world rocked. Okay? So, for example, You know that you're gonna have a problem with that ball is gonna hit the floor and it's gonna bounce. You know it's gonna be on there, okay? You know you're gonna have a situation where you're gonna have a linear momentum situation where they're gonna collide and they're gonna move off together or bounce or something like that. You know you're gonna, maybe, maybe not, they just might hit and bounce, doesn't make any difference, they all work the same way. You know you're gonna have a problem where things are gonna spin and something's gonna land on it and you calculate the new velocity. You know all that's gonna happen, okay? You know it's all going to happen. So work the problems. You have all of your assignments back, you have all of your labs back. So if you've missed some stuff, go back and figure out, wow, what did I screw up? Okay? Even if you got it right, and you go back and you look at it like, ooh, I have no real idea how I worked that problem. Okay? Go back and rework it. Okay? All right. So we're going to get